All right, we have another problem here, an example. And again, my approach to problems will always work, so watch the approach and practice this approach. So we're pulling a friend on a sled on level snow. So here's our friend, we're pulling him. We're pulling, let's see. So she, of course, wants to know what the coefficient of friction is. I know, silly. We're walking at a steady 1.5 meters per second. The rope pulls up on the sled at a 30-degree angle. So I'm just going to call it T for tension. We could certainly call it just F for a pull or P for a pull. We estimate that we're pulling with a force of 75 newtons, so we do have an estimate to that value. Our friend on the sled has a total mass of 60 kilograms. All right. So ultimately, we're trying to find, or estimate anyway, the coefficient of kinetic friction. I know it's kinetic friction because I'm sliding my friend on this sled across the snow. So let's start with the free body diagram. My dot represents the sled with the friend on it. I know that I'm pulling with a rope. I can label this for sure. I still want to use a symbolic letter, a symbol of some sort to represent the force, but we do know the value. We know there's friction because they're asking for the coefficient of friction. So the force of friction we write as F sub K. What we want to find is mu sub K, but they're related. What other forces do we have? Well, force of gravity. The Earth is always pulling towards the center, so force of gravity points straight down. The sled is on a surface, so we do need a normal force. It's perpendicular to the surface, so straight up. Nothing else is physically in contact with the sled, so it seems we have completed the free body diagram here. All right. The tension force, I'll draw it in a different color, has an X component, this pull, and it has a Y component. I can draw the Y component over to the right as well, so that we have our little triangle that represents the force. Now that we have the free body diagram, though, we're going to write out net force equals ma for the X direction and for the Y direction. And again, we're going to do this symbolically for the practice, and also to realize that normal force is not going to equal mg in this case. All right, so in the X direction, we have our pull, so the X component of that tension. We have the force of friction, but it's to the left, so I'm subtracting that. Those are the only forces that have X components. So this right here represents the net force in the X direction. It's not a full-on equation yet, though. We have to say this equals something. Well, according to Sir Isaac, the second law, the net force must equal the mass of this object we're considering the motion for times its acceleration. The net force is determining that acceleration. Okay, I'm going to leave it as is for just a minute. We'll come back and start plugging in stuff we know. In the Y direction, though, I want to write out the same thing. In the y direction, coming back to our free body diagram, we have the normal force pointing upwards. We have this y component of the pull or tension pointing upwards. We have the force of gravity pulling downwards. So all of this together represents the net force in the y direction. And again, to make this a complete equation, we would set this equal to ma, where that's specifically the acceleration in the y direction. All right, let's start plugging in a couple things we know. So for example, we know tension and the angle. So T sub x on this left side, we could write as 75 newtons times the cosine of 30. This x component is adjacent to 30 degrees. The friction force we know is going to be the coefficient of friction times the normal force. So I'm just substituting in what I know to these pieces of the net force. That's going to equal the mass times the acceleration in the x direction. But in this problem, there is no acceleration in the x direction. The reason I know that is revisiting the problem, it says I've been walking at a steady 1.5 meters per second. So a constant speed. Straight line, constant speed, my velocity is constant, so my acceleration is 0. In the y direction, we don't know the value of the normal force. We do know the y component of tension, or the pull, is the force times the sine of 30 degrees. I'm going to go ahead and bring mg to the other side, which actually we know the mass is 60 and g is 9.8. Acceleration in the y direction is 0 as well. If it wasn't, the friend on the sled would start shooting up into the air or sinking down into the ground. I know if I'm walking across a field pulling someone on a sled, that's not going to happen. In this case, then, I actually have enough information to calculate the normal force. But again, the normal force is not equal to mg. And that's because there's that y component of the pull. The normal force is going to be determined by all of the other forces acting in that y direction. So plugging these numbers in, I'm finding that the normal force in this case, 550.5 newtons. This I can now take back and plug in for the normal force in the x direction. The force of friction depends upon the magnitude, how big the normal force is. We've calculated how big it is now. And so we can solve and plug it in. If I take this to the other side, I can now solve for mu. So it's 75 times the cosine of 30 divided by that normal force. 0.118. So at best we have 2 sig figs, so 0.12. Getting pretty close to 0, which makes sense. If we're on snow, it should be pretty slippery. Very little friction. All right. So again, focus on the process. Free body diagram, set up F equals ma for x and y, and then we can start substituting things in.